Alright guys, welcome back. Today we're going to discuss the depletion approximation, and we're going to begin to derive some equations that are standard for any equilibrium pn-junction. So this is what we kind of determined last time. We talked about the band diagram, energy as a function of x in the semiconductor of the pn-junction. We showed through the Poisson Equation and through knowing that our depletion region here is depleted of carriers, which means only on this side we're going to have our ionized acceptors, and this side we're only going to have our ionized donors. So that means our charge is basically this, this function right here, assuming that we have a step function. And through the Poisson Equation, we know that the integral of this, the integral of this is simply the electric field, which gives rise to these, two linear lines. And furthermore, for potential, we use Poisson Equation again. We know the integral of this again, the negative integral of this, that is, we can get, a parabolic line here and then a negative parabolic right here. Negative slope, positive slope, just like that. Our built-in potential is the difference here. That's equal to E F of, or say EI of the P region minus EI of the N region. That's the N bulk, so that would be, this right here would be EI of P, and this would be EI of N. Right, so we figured that out. Now, we're going to go back to these equations right here, and this is charge Poisson equation, built-in potential, which we derived last week. And based off of these graphs right here, we're going to look at some boundary conditions that we're going to use for these derivations. So the first one, called as BC1, and that is the fact that we have two regions of potential and two regions of electric field that we're going to be solving for. The equation for in here is going to be different from the equation in here because we have a step junction. The doping is different over here and over here. So our boundary conditions are going to be that the potential, the electric field in the P region at 0 is equal to the electric field in the N region at 0. And electric field is always continuous, from electrodynamics, we know that. And the same goes for potential. This here and this here are equal at that metallurgic junction. So similarly, phi P of 0, that is the potential in the P region, is equal to phi N of 0. So these are all functions of x. So when I mean 0, I mean at the metallurgical junction, right? So BC2, we also consider at the boundary points. So, at x of n, well, our maximum electric field occurs at the metallurgical junction, but at x of n, our built-in potential is there. So, phi n of x of n is equal to our built-in potential phi bi. Similarly, boundary condition 3, we're going to say that at phi p of negative x of p, it's going to be our potential is equal to 0. It's going by this graph right here. And anything else here? Yeah, we make a reference that. That's basically our 3 boundary conditions that we have. And really, I guess you could say it's 4, if you think about it. But anything else? Yeah, BCO1. That's all I'm back. So, having that over there, what I'm going to do is I'm going to erase this. And we're going to start deriving some stuff. So we're going to start right back at the Poisson equation, right? And we're going to solve for just in the N region, right? So that's d squared phi over dx squared equals negative dp over dx. This is electric field, this is potential, equals what? Charge over our permittivity. Well, what's our charge in our N region? Is just going to be nd plus. So that's going to be negative E nd over E si, right? And this is from 0 x xn In our P region, same thing applies. D squared phi over dx squared equals negative dE over dx, which is equal to the positive E and A over ESI. And this is valid from negative x sub P x to 0. So, what we'll do, let's solve for electric field in both regions, right? We're going to call this E sub n, because it's in the n region, this E sub p, right? Because the equations are, we're going to have different solutions in different regions because we have this abrupt junction. You know, things change abruptly, and so our parameters change, right? We'll just get that off right there. Okay, so you know, we're going to just look at this part right here. Multiply both sides by dx, and then we integrate both sides. So that gives me an E sub n is equal to integral of E n d over ESI dx, right? Two negatives cancel out. Well, that's just going to be E n d over ESI x plus C1, right? So similarly, E sub p of x, right? And I'll write this in terms of x2, is equal to negative E n d, right? Oh no. Yeah, that's correct. Over ESI dx, which is equal to negative E n, oh sorry, NA, my bad. NA over ESI x plus C2. Okay, so let's start applying these boundary conditions. What can I use first here? Well, let's see. First, how about these two right here? Right? Or actually, do I have any other boundary conditions I can use? Oh yeah, you know what? There was a fourth boundary condition I forgot to add. Called this BC4, and that is the fact that that E sub p of x negative x sub p equals E sub n xn, which is equal to 0, right? Because remember, electric field negative xp xn goes to 0 right there, and then as we go into the bulk, the electric field stays at 0. Right? Okay, so I'm going to apply that boundary condition 4, right, to this. So I'm going to say E n of x sub n equals E n d x sub n over ESI plus C1. Therefore, C1 is equal to negative E n d x sub n over ESI. Right? So we're going to do the same thing for this part right here, and then we're going to find that our C2 is simply equal to negative, well, the same thing, negative E n a x sub p over ESI. Okay. So now we have an equation for electric field for the N and P region, and that's going to be E sub p of x is equal to negative E n a over ESI. That's going to be x plus x sub p. Similarly, E n of x is going to be equal to E n d over ESI. Remember, E is our charge, that lowercase e. And then this little e down here, that's our epsilon, that's our permittivity of the material. So that's why I write SI, because we're doing this in terms of silicon right now. So then, you know, this E of n is going to be, you know, x minus x of n. Okay. So, having done that, I'm going to erase this. And now we're going to move on to potential. Well, actually, we're going to solve one boundary. We're going to look at one more boundary condition, and it's going to give us an important equation that will help us later on when we derive the actual length of the depletion region, and that's going to be this guy right here. So boundary condition 1 implies that at the metallurgical junction at 0, because we have a continuous electric field, they're both going to be equal to each other. So I can say EP of 0, and this is BC1, right, equals EP, EN of 0, which is going to be equal to negative E N A over E S I X P is equal to negative E N D over E S I over X of N. So this is a pretty important term right here, and this is something we can verify from electromagnetism, and the fact that we have any time through a uniform material, like silicon, we're going to have a uniform electric, or we're going to have a continuous electric field, and the same goes for potential. So I can rewrite this right here as N A X P equals N D X of N, just like that. Okay, so having known that, now we can move on to potential. So this is the form, continuation of Gauss's law, d phi over dx equals negative E, right? So I can rewrite it. Phi is equal to the negative integral of E dx. So that means that phi in the P region is going to be equal to, let's write 5x, is going to be equal to that. So negative is a positive. It's going to be E N A over E S I integral x plus xp dx. Well, that's just equal to E N A over E S I 1/2 x squared plus x xp plus c3. Similarly, yn of x is equal to negative is a negative, so E and D over ESI x minus x of n dx equal to negative E and D over ESI 1/2 x squared minus x of n plus c3. Okay, let's go back to boundary condition 1 real quick. Okay, so we left off right here. We have a general solution for our potential in the P region, the P depletion region, and a function of potential in the N depletion region, like this right here. So what we want to do now is use our boundary conditions that we already derived to find out what these constants C3 and C4 are. So another thing we can do here is that here. See here. Yeah, so at psi p of 0, it's equal to you know, 0 plus C3. And it's also equal to psi n of 0, which is equal to 0 plus C4. See where I'm going on here? This is actually boundary condition 1, right? So if I plug in 0 for x here and x here, the term I get is the C3, right? And the same here, if I plug in 0 for x here for my psi p, all I get is C4. I'm sorry, this should be C4. Should be C3. Okay, so that's from boundary condition 1, right? So what does that tell us? That tells us that basically, C3 is equal to C4, right? Well, now we can just use one of these boundary conditions and solve for one of these constants. So the one I'm going to choose here is we'll choose boundary condition 3, right? So psi p of negative x sub p is going to be equal to, right? I'm just going to call this C. Right? So psi p of negative x sub p, that will be ENA over ESI over 1/2 x squared. Well, xp squared minus xp, that's just going to be over 2 xp squared plus c3, which is just c. So that means that our c is now equal to negative ENA over 2ESI xp squared, just like that, right? So now we have equation for both terms, right? When I plug this into here, what I end up getting is psi p is equal to ENA over ESI, right? This goes into here. Let me make sure I did that right. Negative, I'm sorry. This should be a negative, right? 1/2 x sub p squared minus x sub p squared would be negative. So yeah, c is actually equal to positive. Okay, that makes more sense, right? So I find my expression for psi of p, and that's just going to be this, and I plug this c into c3 right here, and what I get here is it's x plus x sub p squared. And similarly, when I plug in psi sub n, I get END over ESI, sorry, negative 1/2 x squared minus x sub n, plus ENA x sub p squared over 2ESI, right? So now I finally have my equations for the potential in a semiconductor, in the depletion region of a semiconductor, right? So from this, I can figure out, this band structure right here, and this kind of goes with what we know from the physics already. We know that well, this of course is energy, and energy is equal to negative Q potential, right? So this is we know this is negative. In the P region, we have a negative parabolic. In this region, we have a positive parabolic. Like this P region, this is N region. We connect them together, and we get something like this, right? So now let's figure out one more equation. We have this equation here. We need one more equation to solve for the actual depletion region width, which is W equals Xn plus Xp, right? Very, very important. So what we're going to do here is we are going to use psi n of x sub n, right, which is equal to the built-in potential VBI. So let's plug that in here. So phi, and this is VC2. So psi n of x sub n is equal to, well, let me just plug this in. The x sub n squared minus x sub n squared, again, is positive, so it would be END over 2ESI x sub n squared plus ENA. I'm sorry, that would be, what's going on here? Okay, yeah, we're right. Okay, good. Yeah, everything's good. Over 2ESI x sub p squared equals the built-in potential VI. Right? So I have two equations, two unknowns, right? I have this equation, we're going to call this 1, and this equation, which I'll plug down here, equals E over 2ESI n dx sub n squared plus NA x sub p squared. Okay, remember E is the electron charge, right? Okay, hopefully that makes sense. We're going to call this equation number 2, right? Now, we can actually solve for the depletion which W, which is equal to xn plus xp. Okay, again, this is just a lot of algebra from equation 1. Here I can say that in equation 1 here, I can say that x sub p is equal to nd over na x sub n, right? And then I'm going to solve for x sub p here. Well, if I solve for x sub p here from equation 2, And x sub p here is going to be equal to, it's going to be 2 ESI over E phi BI, right, minus ND x sub n squared, right? And I'm just going to leave this as squared, right? Times 1 over NA, right? So this term is equal to this term, right? Well, this term is equal to the square of this term, right? So I have ND squared over NA squared, x sub n squared is equal to 1 over NA 2 ESI over E psi BI minus ND x sub n squared. Boom, just like that. All right, let's get our x sub n squares together. So I have x sub n squared, ND squared over NA squared, right, plus, right, ND over NA, yeah, that's it, is equal to 2 ESI psi BI over E and A, right? So, and that's equal to x sub n squared. Let's see if I can pull some stuff out. Yeah, I can pull out ND over NA. And then effectively I just get ND NA plus, oh, I'm sorry, ND plus NA over NA. Just like that, right? So, cancel, cancel. So x sub n squared, I'll just write x sub n is equal to 2 ESI psi BI over ENA times NA over ND 1 over ND plus NA, entire quantity square rooted. Oh my god, why algebra? Fuck me. Alright, so leave this up here. X sub n is equal to the square root 2 ESI over E and NA. Oh, well, NA's cancel out. 1 over ND, 1 over NA plus ND, quantity square rooted. Let me double check my math here. No, I'm sorry, there wasn't NA up here. Okay. So obviously I made a mistake. One of these NAs is supposed to be here. If you know, if you watch it again, I probably already corrected with a little bubble, but that's what we're supposed to get right there. So if we, skipping ahead, you guys know how to do algebra up here at this point. If I plug in, if I use this same the same condition here, equation 1, and I solve for xp, I'm going to get xp is equal to also 2 ESI over E, and that's going to be NA. Yeah, that's going to be 1 over NA and D over NA plus ND, like that, right? W equals x sub n plus x sub p, which is equal to, so we combine these two together and you do a bunch of algebra that you should already, should know how to do, what we get is this whole term, which is 2 ESI over E psi BI NA plus NB over NA and B. Okay, so that's W right there. That is the length of our depletion region, right? Going from negative Xn to XP. This is W, just like that, right? It's a pretty important equation. The important thing to know about this equation, though, is this is only at thermal equilibrium, meaning there is, temperatures like, if you're in okay, well, not so much temperature, but depending, but that there's no external voltage supplied to this, right? The only voltage across this junction is your, psi bi, your built-in potential. But what's going to happen here is if we apply a potential, the psi bi, the potential across the region is going to change. So consider just a regular pn-junction. My Fermi level, right? Here's negative xp. Here's x sub n, right? There's my x-axis. So what happens if I apply, this, we consider this a forward bias. If the positive region of the battery is connected to the negative region. Well, what's going to happen here? The positive terminal of the battery is going to inject holes into this region. And then what's going to do is it's going to inject electrons into this region. So what happens? Build up of positive charges here, build up of negative charges here. What's the direction of the built-in electric field? It's pointing towards this. This is your electric field VI, right? Well, now with this battery on here, we get an applied electric field. And what happens is these two fighting together, it's going to lower this barrier height right here. And so what we end up getting, actually, is we break this, we raise up our depletion region. Whoa. And so this is now EFP, and this is now EFN. And the difference between these two, what we call quasi-Fermi level, we call them quasi-Fermi level because the Fermi level by definition is defined at equilibrium, right? So we call this distance here, this distance here is Q V applied. So this here is V applied. So we apply an external voltage and, holes build up here, electrons build up here. This applied electric field works against the built-in electric field and it lowers it. And then our new potential across here is now psi Vi minus V applied. I should say, it was Q, right, times E, electric field E, right? So what we find with this is, and the same thing happens if we flip this battery around, then what happens is, show you up here, then what happens, well, I'll just rewrite, right? So, then what happens is Pn, right? Then, as before, our depletion region actually got smaller, right? Now we do this reverse bias, E, P, E, F, P, E, F of N. These are the quasi-Fermi levels. Now this new thing right here, this distance here is negative V applied, right? So we can rewrite W like this. So W, as a function of applied voltage, V applied, is equal to 2ESI over E psi VI minus V applied NA plus NB over NA and B. Whole quantity square root. So that's what happens when we apply an external voltage, right? So one more thing. What if we have one side of the junction is highly doped and the other side is just regular dope? You know, we call that, like, for example, an N plus P junction. You know, such that ND, well, let's say ND is like equal to 10, you know, to the 18, you know, NA is like, you know, 10 to the 15 or something. Well, this is extremely small with respect to this, right? So we can kind of, you know, rewrite this and write this as the limit in terms of as ND goes to infinity. Because compared to this is infinity. You know, 3 orders larger. Anything bigger than two orders or bigger is considered, you know, N plus P or P plus N, right? So if I did that, well, you know, if I took this, you know, limit as ND went to infinity of W, you know, in terms of our doping NB, right? Well, really, the only term we're concerned about is this right here, you know. So I can rewrite this as I'm going to, you know, divide it, you know, multiply top and bottom by 1 over ND, and I get, you know, NA over ND plus 1 over NA, right? Well, as this whole term, you know, is limit, or I'm going to say it's proportional to the limit as NE goes to infinity, right? So let's go to infinity. Well, this term just goes to 0, and now our depletion width of an N plus P junction is just going to be 2ESI over E psi BI minus V applied 1 over NA. So this is W for an N plus P junction. Okay, so we'll talk more about this in the next lecture, but you know, I finally derived this equation, you know, this equation, and this equation, which are very important, and you know, you can understand a lot from looking at these. You know, remember when we apply a forward bias, meaning the positive terminal is connected to the P side, the negative terminal is connected to the N side, what we do is we lower the barrier of the pn-junction, and the depletion width gets smaller, right? In terms of this right here, right? And if we do a reverse bias, you know, negative terminal to the P side, positive terminal to the N side, you know, what happens is the depletion region, you know, gets larger, and our barrier gets larger, right? So, and that's really how a diode works, and that's what we're going to get in the next part is talking about how the diode works. So that's all we got. Thanks for tuning in.